Okay, good morning, everyone. So we will start soon. Share the screen. Okay. Yeah. So this is what we were looking at. Poisson process with random intensities, and we said that we will be content with giving one example. So you can see some of the different features of this kind of a setup. It's one of the simplest example one can give concerning this type of processes. So it's a counting process, just like a Poisson process, homogeneous or non-homogeneous. It's a counting process. With this thing that it is governed by certain parameter, which in turn is itself a random variable. So given, let's say the random variable capital lambda equal to little lambda, x t plus s minus xs has a Poisson distribution with parameter lambda t. That is this random variable. The time points differ by t units. So it has, just like the homogeneous process, the parameter lambda t for any t greater than or equal to 0 and s greater than. And of course, these parameters will have to vary over positive numbers. So this capital lambda is a random variable taking value in 0 infinity. So this kind of a situation, let's say you may know that it's a counting process, and also perhaps you can determine that it is approximately of this distribution and so on. But then one may realize that that parameter itself is random. Such situations do arise in practice, though we will not be seeing it in this course. So such a process is called a Poisson process with random intensity. So in other words, conditional on this random variable capital lambda equal to little lambda, xt is a time homogeneous Poisson process with arrival rate lambda. Okay. Of course, this variable lambda, big capital lambda, can be discrete or continuous. So we will assume that it's a continuous random variable. And we will denote by small f sub capital lambda the probability density function of this capital lambda. Of course, since this guy takes value in 0 to infinity, this PDF will be 0 on the negative part of the axis. So with this information, then one can say that for any t and s greater than or equal to 0 and any non-negative integer, since this guy is a counting process, these kind of increments will take only non-negative integer values. So probability x t plus s minus xs equal to n. So that is, naturally we will first condition with respect to capital lambda equal to little lambda, because we have a handle on this conditional probability, and then integrate this guy over this density function. So we simplify it even further. Let us assume this capital lambda as one of the most basic and even useful distribution one has seen, namely the exponential distribution, with parameter some theta equal to 0, greater than 0. I mean, theta greater than 0. So this is so the example which we are going to basically consider is xt is a counting process whose parameter, depending on a parameter lambda, which itself is a random variable, and that random variable has an exponential distribution with parameter theta. And given that parameter takes the value lambda, that counting process is a homogeneous Poisson process with arrival rate lambda. Yeah, please note it. I would assume that you are taking down notes, so that forms a major step in this thing of learning. So now, for any t and s greater than or equal to 0 and n equal to 0, then this increment xt plus minus xs, the probability of it taking the value 0 is probability of that taking the value 0 given this capital lambda equal to little lambda, and then since lambda has the exponential distribution with parameter theta, the probability density function of capital lambda is theta times e to the power minus theta lambda, and then integrated over this. And now cap lambda equal to little lambda, given that this probability we know because this has a Poisson distribution with parameter lambda t, and such a random variable taking the value 0, that probability is e to the power minus lambda t. So times this PDF, so that is already here. So you have this. So that you can easily see it is equal to theta can be brought out, and what remains as the integrand is e to the power minus theta plus t, the whole thing times lambda d lambda. So here you are integrating with respect to the variable lambda, and in this thing t is behaving like a constant. So this integral can be easily evaluated. So you have it is theta divided by theta plus t. So with the additional information that the parameter is following an exponential distribution with theta, then the unconditional probability that xt plus s minus xs takes the value 0 is theta divided by theta plus t. In everything there is a verify. So there are a lot of exercises when you try to work out many of these things. I think that is generally the kind of thing in maths. Note that and all, take it seriously. Note that is basically verify that in any course. Note that, observe that, it is easily seen that these are euphemisms for verify that. All right. Now let us look at integers greater than or equal to 1. So going similar this thing, probability x t plus s minus xs equal to n can be written as integral 0 to infinity probability x t plus s minus xs equal to n, given this capital lambda equal to little lambda, and then you integrate with respect to the exponential density with parameter theta. And if cap lambda is little lambda, then this conditional probability, this has an exponential distribution with parameter lambda t, And that such a random variable taking value n is precisely this. 1 divided by n factorial lambda t the whole power n e to the power minus lambda t. That multiplied with theta times e to the power minus lambda theta d theta. So then we take out of the integral all the guys which do not depend on lambda, because lambda is the variable with respect to which you are integrating. So this theta goes out, t to the power n goes out, 1 over n factorial, of course. So what remains is integral 0 to infinity lambda power n e to the power minus theta plus lambda, theta plus t times lambda d theta. D lambda. So now, okay, please note it. We will make a change of variable now. Of course, change of variable is easily dictated by, you have to equate this to some variable. So take r equal to theta plus t times lambda. Then in the previous expression, if you put this equal to r and try to replace this and then d theta and so on with the dr, then you will see what remains outside the integral is here, integral 0 to infinity. So lambda to the power n is this, and of course, this is e to the power minus r, and r dr is this times d theta. So therefore, d theta is this. So again, do this thing of taking out all the guys who do not depend on r. Then you have this expression that is theta divided by theta plus t times t divided by theta plus t to the power n, and then 1 over n factorial times integral 0 to infinity r power n e to the power minus r dr. And you may recall that this integral is precisely, this is a gamma integral. And since the index here is n, it's a integer, this gamma integral also you know that it is gamma of n plus 1. And gamma of n plus 1, one knows that it is n factorial. So therefore, this whole thing is equal to 1. So note that this is a gamma integral, and this is precisely gamma of n plus 1. And one also knows from the properties of gamma functions that gamma of n plus 1 is n factorial. So we have now this process, counting process x, the probability that it takes xt plus s minus xs equal to n, that is given by this. Now, if you put this as p, this is 1 minus p, or the other way around. And n equal to 0 also, it follows that pattern. So it follows, it's clear now that xt plus s minus xs has a geometric distribution with parameter p equal to theta divided by theta plus t for all t and s greater than or equal to 0. If you have not completely taken down this, please do it. And also please check each and every step. So this expression we shall denote by dagger. Okay. So xt plus s minus xs has a geometric distribution with parameter theta divided by theta plus t. So this means this distribution is independent of s. It depends only on t, or rather only on the difference between these two time points. And that precisely is the stationary increment property. So when we started with Poisson processes, the postulates N1 to N6, you can notice that N1, N2, and N4 are satisfied. So now, see, there is a, what is it, very, this thing, conspicuous absence of N3 here. A glaring absence. So now let us see what happens. So towards that end, let's take integers m and n. So because since I have already written like this, the next slide is going to follow a big equation, or rather sequence that's of equations. So probability, we will take the increments, of course, x1 and x2 minus x1. So this is the increment over the interval 0 to 1. This is the increment over the interval 1 to 2. They are of equal length. So consider the probability that x1 equal to m and x2 minus x1 equal to n. So as before, this probability you condition with respect to capital lambda equal to little lambda and integrate with respect to the exponential density, the corresponding exponential density with parameter theta. And when capital lambda is little lambda, we know that the counting process xt is a Poisson process, homogeneous Poisson process with parameter lambda t. So consequently, using that, this conditional probability, we have an expression from our knowledge of time homogeneous Poisson process with parameter lambda. So consequently, and there, this, given this information, the increments x1 and x2 minus x1 are independent. So we know that this probability is equal to 1 over m factorial times lambda power m times e to the power minus lambda, because the time unit is 1. And similarly, this is equal to 1 over n factorial lambda power n e to the power minus lambda. And of course, this exponential density that comes here. So from this, you take out the 2 factorial terms and also this theta. Then you have this, those guys are outside, integral 0 to infinity, lambda to the power m plus 1, that comes from these 2 terms. And then when you add these e to the power minus lambda, I mean, sort of multiply rather, that the indices get added up. So you have e to the power minus 2 plus theta lambda d lambda. So the theta comes from here, 1 comes from here, another 1 comes from here. So note that we have not made any mistake. So again, we make the change of variable, call this as R. 2 plus theta times lambda. So those things I don't have, if I write it here, it would have been possible to accommodate all these equations in one slide. So that after that comma, you will see in the next slide where we have made that change of variable. So this is, to put this equal to R. So this lambda power n becomes R to the power m plus n divided by 2 plus theta to the power m plus n. And similarly, dr divided by this guy is d theta. So again, the gamma integral comes into picture and so on. And that is why you have this one here that comes in the numerator. Okay. Yeah. So this is the change of variable, and the property of gamma function which we have used is here. So we have got this probability is equal to this. Now using that dagger, okay, you can individually calculate that two proper probabilities. Yeah, if you do that, then you will see that gives you this expression. Yeah, please note it. Many of these expressions, just carefully check. So it's clear that probability x1 equal to m and x2 minus x1 equal to n is not the same as the product of the probabilities of probability x1 equal to m and probability x2 minus x1 equal to n. So this process does not have the independent increments property. So an important property of a Poisson process is the independent increment property. So this is not a Poisson process, though it is called generally Poisson process with random intensities. It is not a Poisson process. So that finishes this discussion on this. So I thought I'll start with the next topic, compound Poisson process, but then I decided, okay, maybe we can take it easy. So today we'll put up the notes and also a problem set will be also put up. Yeah, so there's a lot of variety of stochastic processes. So this example is to show that there are even fairly simple looking objects can get complicated.
So just one quick question. So why does it heuristically make sense that uh, this process does not have independent increments?
Heuristically?
Yeah.
Yeah, I have not thought of it that way. One can sort of say that the see that the initial dependence, see in quite a few cases, the initial sort of dependence that is at, see you can view as this the capital lambda equal to little lambda, that kind of a sort of event. It happens, let's say something like at time 0. Okay. So that dependence doesn't disappear. So that sort of that plays a role. So there are certain situations where the quite a few things may depend on the initial distribution and also these subsequent increments. So it may be something like that. Say, for example, there are also situations where the parameter in between changes. That is called switching of parameters. So those things also may not have certain properties which the thing without any kind of change in the parameter happening. Say, for example, in some of the applied situations, a parameter may be depending on external, reflecting external conditions. So if the external conditions suddenly change, then that's called a switching property and things like that. So that kind of dependence doesn't go away, may not go away.
Right. Okay, I think I see your point. Yeah. Okay, thanks.
So anyway, I think I have not, this particular thing I have not thought about. It's a good question. So intuitively, how else can one explain that?
I think like one possible thing maybe like say number of events at the time one, say in between 0 and 1 it has some particular arrival rate, and between 1 and 2 it could have a different arrival rate, as you said, and there is no reason to expect that.
No, but that will reflect in the non-homogeneity. Okay.
Okay.
Non-homogeneous Poisson process is also like that.
Right.
So there, the stationarity is not. Stationarity of the increments is destroyed.
Correct. Yeah.
See, N4, that is N4.
Hmm.
See, stationary increments is a kind of scaling factor. Okay. Say, for example, the couple of exercises which you will see in the one which I put up, you will see that homogeneous Poisson process to non-homogeneous Poisson process under certain conditions are are easy. So that is why our focus of study is basically on the time homogeneous thing. And many of the non-homogeneity very often seems to occur because of certain other conditions. The original process may be time homogeneous, but certain other process which one derives out of it may not be. Whereas independent increment property is a very strong property. Okay. So that getting affected, so that is something like say, for example, in this case, this process example which we considered, so once that parameter is chosen and fixed, and if you have that information, then one does not need to consider that capital lambda as a random variable at all, isn't it? So here the uncertainty factor or this thing arises from, to start with, or throughout the history we may not know. Of course, if you do a kind of, this is our process which can be observed and various quantities can be calculated, then from the data which are what the data which you collect, so then it goes to another realm, the sense that how do you draw that inference concerning that capital lambda takes this value, that will involve some statistical tests. It's like doing statistics with it. So estimating a parameter from the data, unknown parameter. Probably such things are have been studied. I don't know. So such things might have been studied because that's a very natural question. In certain situations, what you are perhaps referring to happens, the parameter after a certain time just changes because of certain external conditions changing. Probably, let's say that parameter lambda is kind of reflects weather conditions. Let us say dry weather means that parameter can be taken as something. If it is wet weather, it can be taken as something. And cyclonic weather means it may be something else, and so on. Or in the context of finance and things like that, that could depend on the external economic conditions. Let us say suddenly some tax laws are changed, or suddenly there is the fall in the value of currency, or suddenly one particular year the harvest is not good. Then the economic parameters change. So in those cases, that basic parameter which may be governing the process, that suddenly changes. So there are processes which have a certain, even in the case of Markov chain and things like that, one can consider. Suddenly after a certain time, that changes, and that might happen at a random time. So you don't have a handle on when exactly it would change, especially regarding weather, economic conditions, and things like that, or harvest, crop failing, and so on. So whereas here, this is something which you have to have some kind of the history of the process at zero. Let's say that decides, once that parameter, that lambda takes a particular value, little lambda, that is fixed in our setup. It doesn't change in between. So that is why one of the main assumptions in the thing we started with is that if capital lambda is equal to little lambda, then it is a time homogeneous Poisson process with parameter lambda, with arrival rate lambda.
Also, while we're at it, and also while we're at it, so does the stationary for proving the stationary increment property also we used this dependence of the exponential distribution.
Sorry.
So is there? Can you hear me?
Yeah.
Yeah. So even for proving the stationary increment property, we used that the parameter was distributed exponentially. So like does something like the memorylessness property of exponential?
Yes. You will soon see. You will soon see that how, I mean, why that exponential property is important, and it is something more general than just for a Poisson process.
Okay.
So soon you will see, maybe after the midsem.
Okay.
Okay. So next we will be looking at compound Poisson processes, which of course many of the applications are based on that. And also I might spend some time on something on insurance model. Okay. So, but anyway, that we will start on Monday. And today, let me stop here. So this thing will be put up, this notes on non-homogeneous Poisson process, and this together with these things. So on.
Thank you, sir.
Yeah. So if you have no other questions, so good that you are asking such questions. I mean, that is some curiosity, some kind of try to guess something, and or ask such a question. Why? See, always I would advise that when you are studying subject, one question to ask is why the hell should I start studying this? Okay, it's in the syllabus, or you have to satisfy certain requirements. Okay, that is a valid answer, but something more than that. So that sometimes, and also many subjects, that reason can be explained only at a later stage, like measure theory, for example. Measure theory is very basic, but the justification for that can be given only after one has seen certain amount of analysis and maybe even probability, because it's a highly technical subject. So, and even historically, measure theory was invented more or less at the last step. Before measure theory and even set theory were invented, all the interesting results in analysis were known. All the Green's theorem, Stokes theorem, Jacobian formula, everything. So many subjects, certain subjects might be like that. Certain subjects, of course, the name itself might be telling you, for example, queuing theory and things like that. Those are of great interesting to engineering students. As a matter of fact, in places like IITs, I think there are for their students, I think perhaps even in BTech and certainly in MTech, there are courses in probability and stochastic processes. And they are, I understand, well attended. So certain things are, the queuing theory is a subject which grew from, or it came into being from telecommunication science. Anyway, so therefore now, yeah, I will end the session and we will meet again on Monday. So take care. Good. Keep asking questions.
Thank you, sir.
Yeah. Take care and see you on Monday. Hope to see more people.